please be informed that this meeting is going to be recorded. That will affect you in case you choose to ask questions. So if you want to ask questions, you can do so anytime in the chat. And also you can raise your hand and we will unmute you in the QA session. So let me briefly introduce you to Embed to Scale, and then we will have our speaker. So Embed to Scale is a project which is mainly EU funded, but also from UK and Switzerland. And the core idea is to leverage embeddings to address a couple of use cases. This includes inference, training, transfer, and retrieval. And here are the project partners. So it's DLR, IBM, Satsen in Spain, Jülich, Synergize, Histosat, Martel, University of Zurich, then the University of Münster and University of Oxford. In this project, we are covering a couple of use cases, for example, forest disturbance monitoring, maritime awareness. This is a resilience use case, crop and stress management, and climate and air pollution prediction, which is driven by University of Oxford. Okay, so we will meet next month, and I will take now the chance to hand over to our speaker, which is Linh. He did her master thesis with us, and she will talk about embedding space matrix constraint fine-tuning. So Linh, please go ahead.
Yeah, thank you so much, Romeo, for the introduction. I would love to share my screen. So it should take a moment. Can you see my screen?
Yes.
Okay, perfect. So first of all, hi everybody. Like Romeo already mentioned, today I'd love to talk about my master thesis, which I did at IBM Research. The topic is embedding space metric constraint fine-tuning of Geospatial Foundation Models. So please, if there are any questions, feel free to interrupt me, raise your hand, and I'll see if I can answer them. So first of all, I would like to tell you a little bit about the intuition that was behind the thesis. So let's begin by a thought experiments. If you are on a plane and you look outside the window and you see, hey, there's like a dense dark green patch, your brain is like, oh, I guess it's like forest. And then you'll fly a little bit away, and then it's going to be like irregular, patchy, and it's probably agriculture space. So your brain don't even have labels for them, but you recognize them again by grouping the concept with similarity. So if something looks like green and dark, it should be probably forest. But the standard classification models don't do that. They are trained just by predicting the right label, which is like a normal way with the cross entropy loss. So the question behind my thesis was, what if we force the embedding space to reflect the human intuition? But we have to first route that into the challenges of observation data. We have, first of all, high intra-class variability. So the forest in the winter would probably look completely different, like the forest in summer. And we have low interclass separability. So, for example, one patch of input data could have both forest and also a highway as well. So the cluster kind of naturally emerging to each other because of the physical nature of observation data. And last but not least, we have the limited label data. So unlike ImageNet, when we have a lot of label data for Earth observation is required a lot of expertise, and is also costly to label data as well. So that is where metric learning comes into place. Its goal is to make the samples from the same class to be close together to create like inter-class compactness is the type groups, but also push the samples from different class be far away. So it creates also inter-class separation. And up above, we see like the normal traditional way with cross entropy loss. The model don't explicitly care about what the cluster looks like. It just care about that decision boundary can be made here, and that's fine with it. So metric learning has a really long and successful story in the literature, both in unsupervised learning and also in supervised learning as well. So the classical unsupervised learning way would be a SIMS-URL in 2020, where they use like two augmented view of an image to create a positive pairs. And through that, they have shown that it can be competitive to like a supervised learning model. And it's a natural extension when we have labels, so we don't need like two augmented views anymore, but we can just use the labels itself to address the positives and the negative in one batch. And that what exactly SUPCON or supervised contrastive learning in 2021 did, and is widely used in many contexts. But how about remote sensing? In the unsupervised learning side, it's also widely used, especially also in the area of pre-foundation model, when SECO use, for example, image from the same geography location, but with two different seasonality, and they also create like possible pairs out of it. Or for example, the vision language contrastive models, which is clip-based, that they use the labels or the description of the inputs and the inputs itself to be like the positive pairs. But for the supervised learning side, the image is a little bit thinner. So we have models that are trained from scratch, but just from based on resonance style. Or when it comes to bigger model, so vision foundation model, they are all trained on image net weights and then fine-tuned on remote sensing data. So up to our knowledge, there is not much literature on fine-tuning geospatial foundation models, and how would like the metric learning will influence the fine-tuning process. And that's what exactly what we want to find in the thesis. So here we have like the really basic fine-tuning process. We have unlimited unlabeled data for pre-training the big encoders, and then use the pre-trained grays to fine-tune them with labeled data. We add a classification head to map the embedding of the encoder into class probabilities. That is exactly the normal standard of what we often do when we train for classification. So how can we incorporate the metric learning loss into it? What we did is that we keep the normal way. So we still have the pre-trained encoder. We have the image level embedding by using global average polling. And we still add the classification head, just a linear layer on top, which will be calculated with cross entropy. But on the other side, we add another pathway. which is a projection head, just a small two-layer, multi-layer perceptron, which map the input embedding into a projected embedding space. In this case, it's 128 dimension, which is then being monitored by the metric learning loss. And then both of them will be combined together into a joint loss, which has a weighting parameter alpha, which we will see later, to control how much of the contribution the cost entropy will have, and also how much left will be there for the metric learning loss. And the gradient just flow back into the encoder itself. Okay, maybe one point here. Some of you may ask why we cannot just use the metric learning loss directly on the input embedding. Why even bother having like an extra projection head here in the architecture? So the decision comes from prior work when they have shown if we apply the metric learning loss directly on the output encoder, it degrades the quality of the embedding itself. So the projection head here acts kind of a buffer so that the encoder can still learn like a really good general transferable features for classification, and the projection head can just specialize itself to fulfill the geometric constraints of the metric learning loss. That's why the architecture was designed like that. So we evaluated two metric learning losses, which the first one is supervised contrastive learning that I will just quickly introduce you in the previous slide. SubCon is the first one, and the second one is called soft nearest neighbor loss, or SNNL. So what are the difference between those two? I've brought you here like an also a quick intuition graph where it show the difference. So first for SubCon, we'll see in one batch, for example, we have here an anchor of a forest patch. It will look in the whole patch, the whole mini batch itself, and pull all of the forest together. So it's like, hey, we're all forest, we must stay close together. So the results would be like a really dense embedding clusters for all the forest. And of course, at the end for all the cluster itself. On the other hand, we have the SNL. It doesn't care much about all the forest samples in the batch, but it just care about the nearest label. So it say, hey, if the my neighbors is a forest, I'm also happy. So the intuition you can also see on the formulation down below. As well, the subcon has summarized before the lock, and the SLL lock all the summarization beside it. Both of the laws introduce one additional parameter, which is here the tau, which is the temperature. The goal is that it control the sharpness of similarities. So the lower the value, the farther the cluster will be away from each other. And because of that is also another like the fine-tune parameter that we have to take account of later on. So what do we ask? We ask, first of all, do these auxiliary metric learning objectives improve classification accuracy over across entropy baselines, across models and data sets? And furthermore, if so, how does that exactly vary with model capacity? Because the intuition is always like bigger model, bigger pre-trained models will already have more discriminated native features that may don't even benefit from another geometric constraints. So that's what we want to find out. About the data set, we use 5 different tasks from the GeoBench classification benchmark. So first of all, we have SOTOSAT. This is a local climate zone classification over 42, I think, cities worldwide with 17 classes. We have BRICAN, is our binary detection task, whether there's a keen or no keen on the picture. I think it's over South Asia. And with just 2 class and almost 15,000 training samples, the cross entropy baseline is already really good. Next, we have ForestNet, is a classification test of what is the primary deforestation task in Indonesia. And this one is quite challenging because it has like a really high resolution with a big number of classes, 12 classes, but just only 6,400 training samples. So the baseline does not work well in this case. Furthermore, we have Eurosat is the classical from the classical Eurosat benchmark, but GeoBench in this case subsamples Eurosat just only 2,000 training samples, so it's naturally already a low data classification. And last but not least, we have PB4G. It is also a binary detection task when it detects whether there's like a solar panel on top in Germany or not. So we chose 2 different Geospatial Foundation models to evaluate on. The first one is Prithvi with 3 variants. First one is from version 1 with 100 million parameters. From version 2, we had 6 million and 2 million and 300 million parameters. The second family we chose was TerraMind with TerraMind Tiny, 6 million, Small, 22 million, and Base 8 with 87 million parameters. So both of the Geospatial Foundation model families had different pre-training mechanism. So the initial embedding space from both families are already different from the start. That was the general training configuration that we use across all experiments. So the goal was, of course, that to create a fair comparison. So all of the backbones that I just introduced was full fine-tuned. And we use Bayesian hyperparameter tuning with a fixed budget of 12 trials per configuration. And afterwards, we found the optimal configuration for each experiment, and we ran that with 10 different seeds to account for the stochastics variability. So if you're curious, we use the TerraTorch. It's the open source toolkit to plug and play with different backbones and heads. So here, for example, I just have to specify what kind of models I want to train on and what kind of heads as well. So for my case, I have 2 different heads, one with the classification head and one with the projection head, and also specify what kind of loss. I have here one cross entropy loss and one metric learning loss. Here, for example, is the subcon loss, and iterate enables you to define how the optimization space would look like. So for the metric learning loss, I have three different parameters I want to tune on. So the learning rate, the alpha, which is the weighting parameter for the join loss, and the metric learning loss temperature, the tau that I showed you in the formulations. So how about the results? Here I brought you the heat maps displaying the performance delta measured in percentage point gain of both losses compared to the baselines. So green is of course always good, and yellow or orange is that we see a negative improvement in compared to the baseline. So out of 60 configuration of loss and model tasks and models, we saw in 42 cases a positive improvement, which is about 70%. But on average, it was just a marginal gain of 0.4 percentage point in average. But I still want to point out some of the patterns that I found out during the benchmarking. The first one, when we plotted a graded in task level, we can see some patterns here. For example, so to set was the one that benefited the most for both losses, and but the confidential interval is quite huge. So we saw that the task like SOTOZAT with 70 classes has quite much of a room for improvement, but it's not stable enough. But on the other hand, Eurosat is also improving a lot in compared to the baseline, but it's way more stable. So it could be that the visual the visually better in Eurosat has contributed here in the benchmark that is more stable in compared to the SOTOSAT data set. The second patterns that we can also tell is that in the blue column, which represent the SLLL, and the orange column, which represents the subcon, SLLN tends to help more in the multi-class classification. So the first three data sets here, which have more than two classes. On the other hand, subcon tends to help better when it's just binary classification test for PG4D and also for Beacon. So here, the global pull and push mechanism of subcon tends to help to separate those two clusters better, and therefore improve the performance of the models. So the second pattern I want to show you is on the model level. So on the x-axis here is the model capacity plotted in the log scale. So on the left side, we have smaller models, which are Prithvi tiny and Terramine tiny. And on the right side, we have the biggest model, which is the Prithvi 300. So we can also already tell there is like an inverse relationship between the model capacity and the percentage gain. So it reflects the theoretical intuition that we talk about. The bigger models are, the less benefits it shows with the joint loss tuning. So the 300 million parameter shows near zero improvement. But of course, we have to say it's not monotonic. So for example, Terramite base, which also just have I think 87 million parameters, which is in the mid-range, shows almost no improvement on the benchmark. So it shows that the raw count of parameters might be not the only factor that is influencing how the losses interact. So the next question that I asked was, how do auxiliary metric learning objectives affect model performance under reduced training data? So I've seen that it's quite unstable under full data. How about if we have less data? It's rooted in the metric learning literature because in the pure world they have found out that specific geometric constraints can get more signals when there's less data in compared to the coarse entropy baseline. So in order to test that, we train TerraMine small on different fractions of training samples. So it was at 10%, 20%, and 50% of the training data. And here we can see already on different data set level, there is no clear trend that we can tell that if we have less data, it's always better, but it's really data set dependent. So Eurosat, for example, is again a really well-behaved data set when we almost see positives improvement when we have less data. But for example, for ResNet, is a clear inverse relationship when we have negative improvement if we have less data. It can be explained by that ForestNet is a hard task. So if we don't have not enough data in one batch, enough positives in one batch, the metric learning could not contribute at all, but just hurts the accuracy. So that where we thought, hey, how about just forget about the downstream task classification accuracy for a moment and actually investigate a little bit more about what is happening actually in the embedding space. And that's why I want to present you two case studies that we did. If you remember from the benchmarking, we took two cases, especially from TerraMine Small on two different data sets. The first one was FirstNet, which shown that in both losses is shown an improvement. And especially for a hard task like ForestNet, 1.88 percentage point was equivalent to, I think, 4.5 relative gain of the baseline. And the second one was PV4G. Is an easier task, and it represents also a binary task that we have seen that subcon shows an advantage in compared to SN and L. So in order to do that, we calculated some metrics of the embedding space, including the retrieval metrics, the CLS score, also pairwise distance between intra-class and also inter-class distance. And also we took the fine-tune encoder and add popping accuracy on top of it to see if the embedding space of the encoder actually improve or not. So here for ForestNet, we saw that subcon was a clear winner on almost every metrics. But one of the interesting thing that I found here, for example, if we look at the interclass and intraclass distances, SNL tends to compress the space. So both the metrics here are smaller than the baselines, but subcon, on the other hand, expanded. And but we have seen here the both laws shows an improvement, but only subcon shows like a better embedding structure here in the space. So what does actually happen, where the improvement does come from? That's why we looked at the delta confusion matrix, which shows the shifts in the prediction probability relative to the cross entropy baseline. So on the left side, we have SLNL, and on the right side, we have subcon. And how to read this chart? If we see here on the diagonal, blue indicates that using the join laws, we have corrected the true probability in compared to the cross entropy baselines. So, for example, for SNLL, we have seen an improvement in the class 6 and class 2, for example. And when it's off diagonal, if it's red here, it also shows that it also shows an improvement on misclassification in compared to the baseline. So SLLN shows like it's corrected everywhere a little bit, and show at the end still a better performance in compared to the baseline. But the subcon, on the other hand, shows like quite more aggressive of redistribution. So it also corrected the class 6 and class 2, but it also hurts the performance of class 7, for example. And in ForestNet, class 7 is like the major class, and class 6 and class 2 is the minority class. So subcon gains the performance by correcting the harder underrepresented class, like class 6 and class 2, but it also by offering the performance that cross entropy baseline already have on class 7, which is like a major class in the data set. So that I want to show you because it's like two way of how they influence the embedding space, but at the end it's both like benefits the downstream classification accuracy in the same way. So on the second case study was for PD4G. So as I mentioned before, in this one is the binary classification task, and subcon show a better classification performance in compared to S and L. But it's really interesting because if we calculate the same metrics again that as we did for ForestNet, we've seen that SLLN is actually a better performance here. So it has better retrieval metrics, and subcon basically quite like doesn't change that much in compared to the cross entropy. So even the popping accuracy improved, but like really small number. So here we can observe like a disassociation between how the losses improve the accuracy, but not the embedding structure itself. So let me put all of them together. What we have found in the study. So first of all, if you have small scale models, joint loss fine tuning would worth a try So it could show improvement in local embedding structure rather than the global embedding space. But in general, it helps rather than hurts the accuracy. But if you already have a high accuracy baseline, for example, 99%, do not need to bother to try and join loss, because introduce like additional parameter for tuning, and also really sensitive to that, and that's why we don't have to use that, and just do the cross entropy baseline is good enough. Another point, but it's not that I want to prevent you from trying it out, because I want to also add some limitation of the study. In this point, we try to have a fair comparison as much as possible, but of course, it is known that metric learning loss is more sensitive to hyperparameter tuning, and having a same budget for cross entropy and for metric learning loss might not be that fair in that sense, because if you tune it even more, it might show some advantages. And the next key takeaways that I want to give you is that the results are really data set dependent as well, as we saw on the graphs. So there is no general claim that could be made that when using specific geometric constraints on the fine-tuning process, it always would lead to a better performance. But it's really depend on what kind of model and what kind of data set are you using or are you fine-tuning on. And one interesting thing that could be good for future work is that the disassociation between geometry and accuracy could be studied furthermore, because we have seen in our study it's not always the case that if we have a better embedding structure with the metrics that we calculated, it always leads to a better accuracy. All right, that's all. Thank you so much for your attention. If you have any question, just feel free to ask me.
Yeah, please raise your hand. We will unmute you or post it in the chat. So I have a question. So why did you choose subcon and SNNL in particular? Did you also consider any other loss functions?
So I chose these two directly because it uses all the positive information in one page. So it's not like some other losses when you have to do hard mining or like explicit finding out the positives in one batch. These two losses just use all the information and then therefore computationally efficient. But of course, is for future work to find out how is this going to be behave with other metric learning losses as well.
Awesome. Since I'm not seeing other questions, I have another one. Did you try different projection head architectures, or did you just stick with this single one setup?
So I just tried this single one setup. It could be that a bigger head, like a deeper one, or could perform better. But is rooted in the literature that they find out that this one architecture with the the one that I apply in the thesis perform best out of the other projection heads. That's why I use this for the thesis.
Cool, thanks a lot. And maybe one last I have, or is there someone else who want to ask? No, I just thought I heard someone. Okay. No. So do you think similar improvements could be achieved with simpler regularization, like dropout or weight decay?
Yeah, actually, I also add dropout in the fine-tuning process as well, but I potentially is also good to have a comparison to other regularizer as well. Yeah, I would not say that is a no.
Awesome. Thank you so much. So no other questions? Okay. Yeah, then thanks so much for your talk, Lynn. I hope you all enjoyed. And the next meeting for Earth to Vec will be on 22nd of May, 3 p.m. Central European Summer Time.